Very well. So if we carry on from page 2 to the next page, the diagram, we wind up on the final output where the microprocessor will be doing most of its work. So to correspond the symbols we have just written, if we go at the top here, my BB bus with my double cross is up here. B0 to B7, the star will be fed at this point. ALE, my tick mark, immediately below it. Then where I put the 0 in, it's fed at this point. LBus enable will be coming from P24, port 24 of the microprocessor. The write enable is my plus sign. The read, my multiplication sign. You'll notice that in between I go back to page number 1 on the read. And the next bunch of lines is my atomic sign. These lines down here are going to be from page 1, which is my address decoder. And immediately below it we have both address and data lines coming from the CBus on page 1. So if I put these two diagrams together, just for an instant here, I'll just show you the symbols. Why I put these symbols together is that I have the 0 here, the tick mark at this point, the star, the double cross, the multiplication sign, the plus sign, the atomic sign. So you can see why I had to get a cross-reference there going. I mean, it's all very nice reading these small numbers, but sometimes it gets quite difficult. So you can see that from the microprocessor on page 2, we have our ports for our LBus enable read and write, output enable and write enable, going to these lines here, through the OR gates, going and enabling each RAM depending on the condition we are trying to achieve. Also, we have to enable the digital to analog converters on the right hand side of sheet number 3. Can you see that? The D2A will receive information from the RAMs when the microprocessor is running normally and transform this information into a DC voltage which will be sent out as a continuous source to the mixer. The only time the D2A is enabled is when pin 10 of each D2A is low, controlled by the microprocessor. So if we take the top one and follow the way back, we will find out that the microprocessor is enabling each D2A. The RAMs, the lookup tables, are 2K RAMs, 8-bit wide for data and 12 bits wide for address. This area here is called the strobe selector. and the final output with all ones here, if we have all ones in this, at this point, will be 5 volts DC at the output, adjusted by one resistor. So all outputs are adjusted by one resistor here. 10K resistor. When the microprocessor is in idle state, when the microprocessor is idle, our output is 2.6 volts DC. When we're in idle state, the output is 2.6 volts DC, plus or minus minimum thing there, 0.13 volts. And when we're in a test mode, what do we get here? We get a 2.5 hertz sawtooth. A 2.5 hertz sawtooth outputs in test mode. I'm going to look for some data now for the program. Yes, please. I'll just check out this. It's clicking in your mind. So, first of all, I'll put some tables on. When D0, 1, 2, and 3, D4 is not used. When D0 to D3 go from 0, 0, 0 we are talking about RAM address. So a RAM address is also considered as being a lookup table. Lookup table 0, lookup table 1, lookup table 2, and lookup table 3. When D0 switches from 0 to 1, we're not talking about RAM anymore. We're talking about offset register. So we're not addressing it, are we? We're just loading data into it. So it's offset register 0, 1, 2, and 3. Just want to verify something, what I do with that. D4 to 15. Okay. So specifically for the offset, we'll be talking about D4 to D15. If you look at your schematic diagram, you'll notice that we're going, I pointed out to you, the offset register on a schematic diagram. Okay, if I use this block diagram, you'll be able to see it better. On the offset register, D4 to D15 for the offset register. And the RAM address MA0 to MA10. Which is still D4 to D15. Okay, so this changes names inside the card. Okay. Here it is D4 to D15, but for MA is MA0 to MA10. So we only use 11 bits, and we, okay. You had a question?
Well, you have to first to address the RAM and then the data in
Yes.
put into it.
Yes, correct. The next time we have only one bit of information that changes. We are now talking to the command register. So D0 to D3 will select either the RAMs, the offset register, or the command register through the decoder. So we have D0 to D3 will either select the offset register, the RAMs, or the command register. At this point, once we've done the selection through these circuits here, we have to give them the proper data. So for lookup table 0 to 3, which is the RAMs, we will have 8 bits, which is D8 to D15, to be exact. A total of 8 bits. For the offset register, this is for data. Zero to 3, we'll have 11 bits, D5 to D15. Actually, it's D4, that's wrong. It's D4. And the command register, 3 bits, because D12 is not used for the command register. Let's look at this one specifically. Okay. Let's look at the 8 bits. What is their significance? D8 to D15. When they're all 0, this is the lookup tables. When inside the lookup table, the data is it's equivalent to 0 volts. D8 being your MSB. When half, so you're going from 0 to 5, so this is 2.5 volts. And of course, when they're all 1, 5 volts. So you could also represent this in hexadecimal. FF for the bottom one, 8, 0 for the top one, 0, 0. Okay? The offset register now. And they start off at D5 and not D4. Okay? Because too big there. 15 there. Yes, they do, because it's not important. Although we have all those bits, we're only going to be addressing to up to 800, remember? No. Offset.
Then you need the D4. Then you need 12 bits.
You don't have to.
Oh, it's a decimal. It's not
used.
Hexadecimal.
Right. Was it hexadecimal that I said decimal, didn't I?
Yeah, you said decimal. Is it hexadecimal?
Yeah, just a minute. That's 1 for you, 0 for me. Okay. So all zeros, of course, is an offset of 0.
When you want to do 800 hexadecimal, you need D4. Or don't you?
You do need D4.
Yeah.
That's right. You do need D4. So this is wrong.
Well, if it is in decimal, it would be right, I think.
You're correct, because this is wrong. Because an offset of 1 is over here, and that's 2.5 hertz. You are correct. D4 is necessary for 800.
And I have another question.
Yes.
If it is hexadecimal, the frequency, you said the 2048 locations divided by 800 decimal, but now it looks if it is 800 hex. How do you compare that figure?
It's 5, 6, 7, 778, 780. Okay, so what do I need to get the value? 800. That's 0. 200. It's got to be hexadecimal. That's 0, 0 all the way. 512. 256. Set. 2. That's 3. 32. So I need that one and those 3. Now hexadecimal would be 3, 2, 0, X.
You don't need D4 and even D5. You don't need it.
Okay. Something I just never thought about. I just kept on saying the same thing like a monkey, and I never even thought about it. Okay.
Yeah. Well, I just.
Everybody's clear on that now? Fully confused?
Yeah.
So 800 decimal is 320 hexadecimal. That is what you match. So you don't even need D5. Okay? You thought you had me cornered, huh? Okay. The command register needs 3 bits, which is D13, 14, and 15. And depending on if they're high or low will mean a different thing. So if D13 is low, you are in test mode. If it's high, you are in normal mode. D14, if it's low, it's a C-bus request. It means C-bus request to the microprocessor. If it's high, it means you sample the lookup tables. Sample tables means normal run. So you would expect 13 and 14 to be high at the same time. You normal sample. And D15, when it's low, it's a reset to the 8039. And when it's high, it's run. And we'll stop here for lunch. So the program, the handout I just given to you contains a program listing, program flowchart, and the first few pages of program explanation of the EEPROM that controls the microprocessor 8039 in the CSS card. And I have some few notes that might not have come out because they were in blue on the original. So we'll go through the introduction and so on, and I'll point out a few things to you. The EEPROM, the program is EEPROM resident on the card, the CSS card. The program generates 4 continuous sounds by taking samples from 4 lookup tables. And the table can be loaded from the host computer via the C-bus. A sample taken from each lookup table every 200 microseconds, 195, which is a sampling frequency of 5 kilohertz. The frequency of each continuous sound, 5 kilohertz is wrong, it's 2 kilohertz, not 5. 200 microseconds is 5 kilohertz, that's right. But we only go up to 2 kilohertz. The frequency of each continuous sound is controlled by the host computer via the C-bus by supplying the offset to be used in calculating consecutive lookup table addresses. A test facility can be selected by means of which the 8039 loads each lookup table with 1. This selection produces 4 sawtooth outputs of 2.5 hertz. Okay. Now they give you the system schematic. Now these system schematic numbers are not your system schematic numbers. Okay, those the CSS cards is 115. Well, it is 530 11268. It is correct. Oh, good. Because the reason I'm not mixed up is I've been teaching CF18, Lufthansa, K11. So there's each contract has a different number. The program description can operate in 2 modes, test and normal. The functions performed by the 8039 can be summarized as follows. Initialize, that's what is scribbled in handwriting, which is initialize, the test program, the normal program, and the interrupt service routine. And then they go on describing it. Initialize caused by a reset on D15. D15 has to be low in this case. It does 3 things. It clears the internal registers R4 to R7. So those are the 8039 registers, not the card. In band 0 and band 1. And this initializes the 4 lookup addresses to 0. It writes 80 hexadecimal in address 0 for each lookup table and latches 80 hexadecimal into each DAC, resulting in 2.5 volts DC. It then reads P27. Reading P27, if P27 is low, it executes a test program. If P27 is high, it executes the normal program. Okay, P27 is on the microprocessor itself, and it's a port. Well, I've got it here, but I'll put it down. P27, depending on if it's high or low, it is your test line on your circuit diagram. The test program itself, what does it do? It loads in a 256-step staircase into each lookup table. Each table will contain the following information at the end of lead. Now what happens is that table address 0 to 7 will contain 255. It's for data. So you'll go through 8 addresses. 8 to 15, 254 for value. And so on, down to up to 2047, which contains a value of 0. Okay? Now, the second step, it enables the external interrupt, and then enable local bus access, LBus, to the lookup table. It will read the lookup table, number 1, latch the sample into the DAC, number 1, and output it automatically, and then will repeat itself for step 5, 6, and 7 for the next 3 tables. Then it will increment the lookup table address and do it again. That's the test program. Any questions on that? Okay. That is for the test program. Either you can initialize it manually with the push button and the links, or you can do it with the DAC bus test set by flipping D15 to a low, which will go to the command register, and the command register will then inform P27 that it is in test mode. Normal program. In a normal program, the microprocessor waits for the C-bus access request indicated by an external interrupt, and this will be felt on which one? Which is the reset on pin 4 of your microprocessor. It will enable the interrupt and execute the interrupt routine. Now, step 3, execute the interrupt routine. Of course, we'll be mentioning that later on. There is a description of the interrupt routine. Once it executes the interrupt routine, on step 4, it enables local bus access to the lookup tables. It will read the lookup table 1 at current address and latch the sample in DAC 1. It will repeat step 5 for tables 2, 3, and 4. And at step 9, it will disable the local bus access to the lookup tables, fetch the offset for going back to RAM number 1, and add this offset to its current address, which gives it the new address. Then it's going to do this for the other 3 RAMs and go back to 4 continuously. This is normal run, as long as it's not interrupted, it will carry on doing this all the time. Now, if an interrupt occurs, it will save the accumulator, save the local bus access status, disable the local bus to the lookup tables, and enable the C-bus. Why? Why will it do this? Because it's been interrupted. It knows that the host computer wants to load in some data. So it has to enable the C-bus to do that. Now, this will normally occur at the beginning of the download of running the simulator, because once it's initialized, it'll carry on all day. Step 5, it waits for an end of C-bus access indicated by an external flag coming from the command register, and disables the C-bus, restores the L-bus access, and restores the accumulator, and carries on, goes back to the normal routine, which is normal routine step 4 on a normal program. Am I going too fast? So this is the basic step. You have 4 programs: initialize, test, normal, and interrupt subroutine. The next page, you have a flow chart. Okay, so there you have your initialize 8039 with a reset D15 being low. Initialize the lookup tables and the DACs. It then reads port 27. Do I want to test, yes or no? If it's yes, it goes to the next page 1. If it's no, it goes to number 4, which is on page 8. So let's carry on with a yes test first of all. So the next page, it does exactly what we mentioned before. Load lookup table, enable external interrupt, enable local bus access, reads the table 1, latches a sample into DAC 1, reads table 2, latches sample in DAC 2. Next page 7, reads table 3, latches sample in DAC 3, reads table 4, latches sample in DAC 4, increments lookup table, and goes back to 2. which is page 6. Now I will do this as long as it's on test. If we did not want to test, we go to page 8. It reads the interrupt flag. Is a flag low? Yes or no? No, it will loop upon itself. If it is yes, there is an interrupt, so it has to enable the external interrupt. So it will enable local bus access, read the lookup table 1 at current address 1, latch to sample in DAC 1. This carries you to page 9. It will do the same for table 2, 3, and 4, and send you back to number 6, which is page 10. Fetches the offset 1, address 1, which is the old address plus the new offset, fetches offset number 2, address 2 is equal to old address 2 and the offset of 2, and so on. And 7 sends you back to page 8, where it will do the same thing again. Now on page 11, on its own, the C-bus interrupt. What happens when it sees an interrupt? It saves the accumulator, saves the local bus access status, wants to know where it was, what it was doing when it was interrupted, disables the local bus, enables the C-bus, reads the flag. Is the flag high? Yes. It goes on to page 12. If it's not high, it comes back and reads the interrupt flag. So on page 12, it will carry on its interrupt routine by disabling the C-bus access, restore the local bus, restore the accumulator, and return to its normal program. Now the initial interrupt, there will be a 21 microsecond delay, but after this, if there are any more interrupts, there will practically be no delays. The reason why there's a 21 microsecond delay is we do not want to corrupt the data on the C-bus or on the L-bus. But if there's a small chance that it might occur. The fact that we're coming back to it 195 microseconds later will not be apparent to the ear. The fact that we're changing from C-bus loading to DAC bus, it might be, you might be loading the DAC with C-bus information. It will not be apparent to the ear. Okay, the next page is your source file. No, that is your source file. That was your source file. 115769. Yeah, the next page, this page here, is the top page of this, what I just given you. It was just mixed up in the print. The next one is a program listing. Now the program listing is the same thing, but it's in assembly language. If you go to page 1, you'll notice that it has a program description, and this program is in assembly language, and you have a few right underneath macro you have LBO enable, LBODS, which is disable, L-bus output disable and enable. I've written it down with a little arrow that explains that. So going through these, you also realize that H, whenever you see H at the end of 3 or 4 numbers, it always means hexadecimal. Now let's see. If you go to line number 137, line number 137, you'll notice that on the right hand side I've put down OS is equal to offset register. That's an explanation of OS LO enable. So we would have offset register low enable on line 137, which comes out of port 42. So that we enable those. Remember, we have 12 bits to put onto an 8-bit bus. We either have the 8 LSB and the 4 MSBs. Okay, next page. 2, 3, 4. Normal program. There's no other notes that I can think of in here. Okay, so that is the EEPROM program in assembler, an explanation for the microprocessor. The next few pages are copies of an Intel book which show you a few of the components that we have on a CSS card. The first one is the input-output expander. It's an 8243. It gives you the architecture of the chip. After this, we have a decoder. Shows you the pin layout, pin configuration. One of the decoders we have in here. And that would be, let me see if the chip is there. H9. $32.05. Yes. The chip involved is KK40, KK50, and KK60, which are these three latches here. These three. So you have, it's for your decoder from D0 to D3. How the pin configuration works here for these three chips. Finally, I have printed out the microprocessor, the 8039. So an 8039 or an 8049 is the same except for its crystal clock frequency. And you have certain port definition and instruction set for it, although that's not necessary for you. So what happens to you when you determine that it is one particular CSS card that is not functional? You have put the card onto manual, you are single stepping through the card, and you find out that there's a problem. Now it's the microprocessor that's wrong, or it's the EEPROM that's wrong, you don't know. Well, first with the LEDs, you'll be able to determine if your PC is correctly going through the steps. And if it's your EEPROM, what would you do? What is the KLM's policy to repair? Repair to chip level? First of all, you replace the board and your simulator functions. Now what do you do with that board? Do you send it back to...
It depends. If you can repair it,
okay. So how would you go about ordering another EEPROM? Because
we have copies of all EEPROMs.
We have copies of all the EEPROMs.
okay, so you know that I have an EEPROM on the CSS card. Of course, the 8039 is used several places through the system. So So you want to have this particular program, not just any. So you'd have to specify that EEPROM. How do I specify that EEPROM?
Yeah, I think it will have a number.
Okay, it has a number. Also, you could also specify with the numbers situated on the cards themselves, like on your system schematic, not your system schematic, but your schematic diagrams. You have a number at the bottom here, correct? So that is the, you have a number at the bottom of the system schematic diagram, and that would be one of the part numbers. Now, has anyone, you familiar with the CAE numbering system? Okay, so you realize that most of the time, let's say we have 115.530.011268. Just a little refresher. Of course, this is the CSS, for instance. This is the tab number. These numbers here will mean something. Okay? This one means schematic diagram. A 2 is your top drawing for your assembly, your and so on. An 8 is a performance spec. A 9 is for our test specs to test these cards for us, and so on. So you'd be going to a number like this and ordering the part for it. Because in this case we only have one EEPROM, so there's no problem. Okay, so that covers the... And the last page is the DAC itself, its pin configuration. It is an NE5018, and you can see the application of it. It receives 8 bits and converts that to a digital voltage. Sorry. Now I can't remember what company. SENE. I can't remember now. I don't remember the company that manufactures that particular chip. Okay. So that takes care of the CSS card. So this morning and just now we finished talking about 2 cards, the CSS and the RSS. And these cards are considered to be the digital portion of the sound system. So our maximum frequency output will be 2 kilohertz. It is possible to test these cards through the DAC bus test set and manual. You can also disable the card, put it on test mode, and insert your own signals if you wish. What is the next card we're going to see? The mixer. I had it here somewhere. Sound mixer. Now, where's the sound mixer situated in the overall block diagram? We have 6 sound mixers, and each random sound synthesizer and continuous sound synthesizer feed in to every single one of them. What would you think is the purpose of this? Why would we want to feed all the channels to all the cards?
Because a certain sound is made of several signals.
Yes, but remember the final result.
To get everywhere the same signal.
Exactly.
Sound.
Exactly. So what's going to happen is that we want all the speakers to reproduce, let's say, for aerodynamic hiss. But let's say, an Airbus, how many engines? 2?
2.
A310. Let's say the port engine explodes. There's a bang, I don't know. Although the sound will have to come from the left at maximum amplitude, the same sound will have to be reproduced in the other speakers as well, but at a reduced level, to give you the impression that the cockpit is full of that sound, but has a certain direction as well. So that's why all these signals are sent to the 6 mixer cards, to the 6 sound generators, and the 3 dual power amplifiers, so that all the speakers receive all the mixture, plus or minus amplitude, to give you an impression of direction, of fullness around it. Okay, so that's why we have to feed them all to the 6 of them. So what does the sound mixer look like? On one of your handouts that I gave you, page 11, figure 4, basically, very simply, the sound mixer is your dotted line. Now what feeds into the sound mixer? Okay, I'll give you a chance to get those diagrams. So on your left, you have 3 CSS cards. So you can put a note there. There's 3 CSS cards and 3 RSS cards for a total of 12. And I've put down 16 because it can be a maximum of 16. KLM uses 12 lines into D2A. Now, you'll notice that the CSS goes out through a summing amplifier where all the 12 sounds are blended together, and then sent out of P2 pin 7 into the sound generator through a filter which is completely independent of the sound generator, back into the mixer at P2 pin 9. Oops, I moved it. And then summed again, where is once again controlled and sent to the sound generator. The RSS feeds in 12 lines through the D2A, through a summing amplifier, into the bigger summing amplifier for its final output, where all these signals are blended. Now you'll notice here right in the middle, there's one D2A that is all on his own. He gets his signal from a voltage reference out of the D2A, back in and into the summing amp. And this one will be enabled only when I am testing this card. It will be feeding the signal on its own to the tie point past the last D2A, down to an A to D, back to the C bus. So what do we have to send to the mixer? We send it some signals, and in the middle between the two cards, the RSS and the CSS, through the C-bus, we send information to two latches. One is the address latch, controlled by A15 being high, and the other one is the data latch, controlled by A15 being low. You'll notice that between these two latches we also have DA. Once these signals are fed into the latches, they are then sent out to the appropriate D2A. How? Well, this decoder here will have 1 to 16 outputs, individual output, because we have 16 D2As, although you'll be using 12. And also going down to 17 to 32 for the 16 other D2As. Output 34 is going to go to D2A test, and output 33 is going to go enable the last D2A for final amplitude control. When we want to test this particular circuit, at the same time as output 34 is enabled, we will have a DR felt present at the A to D, so that our DC voltage is reconverted back to an 8-bit word sent back to the C-bus. Have any questions on this? Pretty simple, isn't it?